Here we will talk about the environmental consequences, leaving aside human beings for the most part for now. So, we talked about how the warming is much more intense and concentrated at the poles. So that's going to be South Pole, Antarctic, and the North Pole. We'll notice, right, so at the South Pole we have a continent, an actual landmass, which has an ice sheet on it, but also these so-called ice shelves that extend out into the water. At the North Pole, there is no continent. This is sea ice. However, there is Greenland, which is a big continental landmass with a huge ice sheet up in the Arctic. In other words, if you were to go to the North Pole, like into the Arctic here, what you would see is sea ice. This stuff is melting. It is melting at a rate that is kind of mind-boggling. Glaciers here are going to be separate from ice sheets of Antarctica and Greenland. That's why glaciers are put on here separately, even though ice is ice on some level. You'll notice, right, so this is cumulative ice mass lost, GT. GT is an abbreviation for gigatons, so that's billions of tons. So cumulative ice loss in just the last 20 to 30 years would be something like 5,000 billion tons, which is a lot. We have sea level rise on here as well, but we'll look at that again in the next chart. A lot of it in Antarctica is coming from the West Antarctic. The eastern part of it is mostly okay. There's a ton of ice loss in Greenland, a ton of ice loss in the Canadian Arctic, and a ton of ice loss in the Andes and in the Himalayas and other big mountain ranges, which do have glaciers owing to their elevation. As a result of all of this ice melting and this phenomenon of thermal expansion, where because the oceans are getting warmer, the water expands, essentially. The molecules are moving faster, and so they tend to spread out and move further away from each other. Those two forces combined, loss of ice and thermal expansion, are driving sea level up. It looks a little bit, I don't know, not so bad, right? 3 millimeters per year, but when that is happening around the entire globe, considering how many people live along the coast, and when it is every single year, and as we'll see, a lot more exaggerated and impacted in some places than others, this ends up being really hugely significant, right? This is also one of those trends where you can pretty confidently tell what's going to happen in the distant future. In other words, you can project and predict this one outward pretty reliably and see that it is going to keep going up and that that is going to cause massive issues for human development. Oceans are getting more acidified, right? So something like 50% of the carbon dioxide that is put into the air is absorbed straight into the ocean, right? It dissolves in, it becomes this thing called carbonic acid, which lowers the pH of the entire ocean, essentially makes the entire thing more acidic. Something to be aware of when it comes to ocean acidification is that what looks like a very small change can actually be a lot more significant than it looks. Why? Because pH is an exponential scale. So a drop from 8.2 to 8.05 in pH, which is a pretty reasonable estimate for how much pH has dropped since the start of the Industrial Revolution. You might take a moment to pause here and try to think to yourself, how big of a percent change is that? Now, we can do the math on this. This is like a 50% change. I'll put it into a note. This is like a ocean that is 50% more acidic than it was before. It's misleading because this is an exponential scale, right? But it really is that big of a change. Marine organisms of all types, things that have shells, which is a lot of them, or things like coral that are made out of calcium carbonate, they will dissolve in acid. I mean, this is the reason why, old gravestones dissolve in the presence of acid rain, right? We have our healthy shell in the organism up here, and the not-so-healthy shell on the bottom. And when this is applied on the scale of the entire ocean, and getting worse over time, poses massive ecological issues, consequences. Other environmental consequences related to evaporation and precipitation, right? So, we got to separate out evaporation from boiling, right? So boiling would be like a total phase change. You heat up water so much that you turn all of it into gas form. Evaporation is mostly, right, this kind of escape. So molecules that are at the surface get heated and evaporate. This is happening constantly. I mean, if you leave a glass of water out in the sun, right, and go inside and wait a week, right, it's going to be completely gone. It didn't boil, but it evaporated, right? Molecules get heated, become mobilized into water vapor, and then they leave. If you have higher temperatures, more heat energy, then you cause the amount of evaporation to increase. So more heat energy in to the ocean or anywhere in the entire world, and you get more evaporation as a result. And because we have sort of supercharged this part of the water cycle, you get more intense precipitation, right? More extreme events like storms and cyclones, right? Because you have put more energy and driven more evaporation through the system. This can be consequential for many reasons, but one of them that we can kind of root out, right? I've heard this before, this idea that, okay, there's going to be more evaporation, and so there's going to be more rain, but the water doesn't disappear, so where's the problem? There's a number of problems with this, right? Part of it is that whenever water evaporates, right, and becomes water vapor, there is no guarantee whatsoever that it is going to come back down as rain in the same area where it evaporated. So this is a watershed basin map of the United States. What this means is that a drop of rain that falls anywhere in this entire pink area, any drop of rain anywhere in there, will eventually make its way to the Mississippi River and out. So we can see the Mississippi River here, giant. This is the Colorado River watershed domain, right? Every river in Arizona will sooner or later make its way to the Colorado River, right? Every drop of rain that falls within this boundary will sooner or later make its way to the Colorado River and out into the Gulf of California. Part of the problem with having increased evaporation and precipitation is that whenever water evaporates here, there is no guarantee that it comes back down inside this same watershed. It can go elsewhere, it can cause extreme events of drought, flooding, and more. The final thing that I would want to talk about here is computer modeling. We are not going to spend very much time on the computer modeling aspect of climate or projections and predictions into the future, but we can talk about how this is done, right? So essentially, you have a computer model that breaks down the Earth into these little cells, right? Little blocks. And to be clear, these days, the individual blocks are way smaller than what you see here. In other words, the resolution is a lot better than what you see here, right? And the idea is that you go into each one of those blocks and you figure out the forces, okay, of precipitation and evaporation and heat flux, right? And how much is going to be reflected versus absorbed. And you figure out all of those physical factors in each box and the relationships between the boxes. You run a computer simulation and you get some idea of how climate is going to change into the future. Our approach here is largely non-predictive. In other words, not going to emphasize predictions and projections for reasons that we will see. But it's important to know that using computer model, you can make forecasts, and that these forecasts have gotten much better over time. And as a result of this kind of computer modeling and forecasting and projection and prediction into the future, you can come up with different scenarios for different kinds of warming or warming tracks that the planet could be on, right? So one such track would be 1.5 degrees C of total warming. Another track might be 2 degrees C, another one might be 4 degrees C, another one might be 8 degrees C. And this will come up extremely prominently whenever we go to talk about climate as a global issue. But first, we're going to talk about paleoclimate and the way that Earth's climate has changed over time.